Salaam alaikum. Can you hear my voice correctly? Can you hear my voice? Okay. Uh, in the last lecture, we talked about uh, two different algorithms to find frequent patterns. We introduced a priori and also FPGrowth, and we show that how we can find frequent pattern using these algorithms. Okay. Today we will continue our course. As we can see in FPGrowth method, FPGrowth use a tree structure, so it can grows recursively. We can use recursive functions to find different patterns, and for each frequent item, we can construct its conditional pattern according to the structure of FPGrowth algorithm. To find new conditional patterns and search whole tree. Okay, but there's a problem here. What will happen if the size of FP3 becomes large and when we cannot fit the FP3 in the memory? What we can do at this time when we have not enough memory? To solve this problem, firstly, we can divide our data set or the DB, the database, into some parts, and then create some small FP3s for each of those splits. Then we can combine those parts together to create a longer FP3 and finding other conditional patterns. So in using this method, we can solve the problem solve the fitting problem, fitting in memory problem. Please be care that memory limitation is one of the main problems in most of applications of data mining. Most of times we have lots of problem with memory and size of memory, especially when we are when we work with big data. So splitting the data set into smaller parts and then working with those parts instead of using the original big data set is the main and maybe the primary method that we can use So not here, but for all data mining techniques, we can use this strategy, splitting a data set into a smaller parts, and then working with those parts, and finally uh, integrate the results, the sub results, into a bigger one. Here we can use this, a similar method for FPGrowth when size of our database is large, and we cannot fit the data set in the memory. How we can project our data set into smaller parts? We have two different choices to split the data set. We can divide a data set using a parallel projection method, parallel projection techniques, or we can divide a database using partition projection. But what is the difference between these techniques? When we are talking about parallel projection tries to project the database according to frequent items in a parallel manner. In this case, we have some partitions, and then we are working on those partitions parallelly. The total process is done in parallel. So to do this method, we need to use strong and powerful hardware and platforms. But a simpler technique is using partition projection technique. Here, instead of projecting database according to each frequent item, here we partition the database according to the ordered frequent items. And then we only need to process those sub-partitions that they are not processed. This technique does not need a parallel processing. So partition projection, it seems partition projection is simpler than parallel projection with less cost than the parallel projection techniques. Here you can see that in parallel projection, we need lots of memory and especially lots of disk space. But partition projection can save this method. You can see here in parallel projection, we divide the data set according to the frequent items, for example, P, M, B, A, C, F, and rest of items, and then we should work on them parallelly. For example, here for M project DB, for F cap, we have other subsets, for example, FC and also F. M is combined with A, M with A and C. Here you can see that we have to use lots of memory to save all of these frequent items in a parallel manner, and their subsets, also their subsets. So this technique is costly. It's fast, but it's costly. Excuse me. Here you can see a performance evaluation. Here, when we use parallel projection techniques, we have to find all frequent items in a parallel manner and work with them simultaneously, because all partitions should be processed parallelly. These techniques needs lots of memory and lots of disk space, because I couldn't store all of these parallel partitions in the main memory. So I should save most of these partitions into the hard disk. So this technique needs lots of disk space. Instead of that, when I'm working with partition projection, just simply I'm working with some ordered frequent items. I can work with one frequent item and complete that, and then I can work with another item. Here you can see a performance evaluation between FPGrowth and a priori. To do this, the others use here you can see for different thresholds. You can see that a priori uses more times than FPGrowth. The runtime for FPGrowth is too small. So this image shows this figure, this plot shows that FPGrowth is faster than a priori. Here in the right figure, in the right plot, the others uses the same data set, but with more records. Here they use 100,000 records. In the left plot, they use just 10,000 records, but in the right plot, they use 100,000 records. So they just want to compare the FPGrowth with three projection techniques. As you can see here, for a small value of support, still the FPGrowth acts better than tree projection for a small uh, support thresholds. But when the support threshold increases, we can see that both of those techniques act similar. Nuratnan, you cannot hear my voice? Nuratnan, can you hear my voice? Okay. Here, my Nuratnan, Nur, the quality of my internet link to the server is very good. So it seems you must check your link, your internet link. Okay. Maybe someone asks why FPGrowth is better than tree projection. Why it's faster than tree projection. Why? Please note that here FPGrowth tries to create the whole whole FP tree in the memory, and it works only one times with the memory. So it needs using memory and working in memory is lighter than working with secondary memory and hard disks. Here you can see that when we are using tree projection techniques, tree projection tries to use disk space. So you can see that it uses more runtimes. It's slower than FPGrowth. But as soon as we increase the support threshold, also here in the left plot, we can see that as soon as we increase the support threshold, we can see that both algorithms act similarly. And maybe here in the left side plot, you can see even that the a priori technique acts better than FPGrowth. Here for support threshold of 2, we can see that both algorithms act similarly. But why? To answer this question, that why these methods working similarly when we increase the support threshold, we should note that just fewer number of records have big support values. So when we start to find frequent patterns, I'm repeating again, just a few number of records has higher value of support. So when we increase the support threshold, most of patterns will be removed from the process, from our process to find frequent items, because they cannot reach to the minimum support threshold. They will be removed from the process, and so the algorithm will be finished very fast. What does this slide shows? This slide shows that when we are working with frequent patterns, when we are looking to find frequent patterns, if size of our data sets is small, we can use well-known algorithms such as FPGrowth to find frequent items. We can use them directly. Here you can see that for 10 kilo records, the maximum runtime of FPGrowth is something about 45 seconds. But for 10 kilo records, the runtime is about 150 seconds. So if size of our data set is small, we can use well-known and primary algorithm to find frequent items. But when size of our algorithm increases, we cannot keep them in memory. And also we have to use more time. We have to spend more time to find the answers, to find the frequent patterns. So for larger data sets, we have two options. We have two choices. The first choice is using projection trees. We have two choices. The first choice is using projection techniques, because we cannot keep large data sets directly in the memory. We have to use projection techniques to keep them whole datasets and work with the datasets. And the first choice and the second choice is using higher values for thresholds, for minimum thresholds. Here you can see for threshold 2, minimum threshold 2, you can see that there is no difference between FPGrowth and tree projection. And in the left plot, you can see a priori technique is even better than FPGrowth. So keep in your mind, for larger data sets, don't use small support values because of these limitations. You need lots of memory, and also you have to spend more time to reach the answers. Maybe sometimes maybe you need to spend some weeks or months to get the answers. So you cannot use small value for supports. But as I can see, FPGrowth can act better than and faster than a priori and some other other techniques to find frequent patterns. Why? Because it uses a divide and conquer techniques. It's trying to look the database one times and then creating a tree. In a priori, in each step, we have to scan the database. These scans need lots of time, spend lots of time. But here, we only need to one or two database scan. Also, if we change the structure of pattern growth approach with partitioning techniques, we can clearly work with smaller database using FPGrowth to find larger frequent patterns. But maybe you say that, okay, for example, here, the tree projection technique uses a similar technique to project the data set into smaller parts. So why FPGrowth is better than that? FPGrowth has different factors to work well. For example, it never generate candidate items. It tries to create a FP3 structure from the database. So the tree, we can say that this tree is a compressed version of the dataset. It never repeat the database scan multiple times. It's just use one or two scan. To create a fit tree structure, we are using local frequent items to find and create FP trees and finding frequent items. We never need to search the whole tree, for example, to find frequent items. Just locally, we can follow some passes in the tree to find and calculate the support value for each frequent items. So it's a good approach, good technique to find frequent items. Also, you can find some edited version of FPGrowth, for example, FPGrowth Plus in the internet. You can find the source code of these algorithms in the internet. Card partner, AFOPT, TD close. There are other versions other versions of FPGrowth that tries to reduce the overall overhead process of FPGrowth. Here you can see other versions of FPGrowth, for example, close set, prefix span, GSpan, convertible constraint, H3, H-cube, Maple, and other techniques and methods developed by different others. But in all of these proposed techniques, we can see the pattern growing techniques or pattern growing methodology has been used. So it's a good option in this case. The third algorithm to find the frequent patterns is ECLAT. But what is ECLAT? In API and FPGrowth, we try to find frequent items horizontally. What does it mean? It means that I'm searching a record to find frequent items to calculate their supports. I'm scanning record by record and calculating the support values. Excuse me. In eClat, we are looking for another techniques. Instead of working in horizontal manner, working with finding frequent item sets in records, in eClat, you are trying to explore the data sets vertically. What does it mean? For example, when we are talking about a vertical format, for example, I'm looking for frequent pattern AB. It's a frequent pattern, for example. I'm looking for the support count of this pattern AB. In eClat, we are using a transaction ID list or TID, transaction ID list or TID. For example, TID of AB, TID of pattern AB is set of, for example, T11, T25, and the rest. The TID list here is a list of ID of transactions that I can see pattern AB in those records. For example, in transaction 11, I can see pattern AB. In transaction 25, I can see pattern AB. So in TID list, I can see ID of those records, those transactions that they consist pattern AB. It means that I'm dividing the database in a vertical format instead of working with values in the records. Here I'm working with ID of transactions. I'm trying to find frequent patterns based on vertical intersection between different transactions. What does it mean? For example, let's suppose that T of X is equal to T of Y. The TID list of X is similar to TID list of Y. It means that I can see pattern X in some transactions. This list, in this list, I can see pattern Y2. X and Y are seen in a similar list. Sometimes we can say, for example, T of X is a subset of T of Y. This means that if I see pattern X, then I can see pattern Y2 because X is a subset of Y. In other words, transactions that they have X, they have Y2. Okay, using this list, this TID list, I can create a diff list, diff set or a differentiated set or a difference set. For example, T of X is transaction is a list of T1, T2, and T3. It's a set consists of 3 different items, T1, T2, and T3. And T of XY for pattern XY. Pattern XY is presented in T1 and T3. So what is the difference between T of X and T of XY? Simply, we calculate diff set X, Y, and X, which is 2. This means that T of X and T of XY are similar, but their difference is transaction 2. In transaction 2, we cannot see pattern XY. We can see pattern X, but we cannot see pattern XY. So the diff set is T2. So simply we can count, we can create this TID list, and we can count diff sets between different patterns to find frequent patterns. For example, here I can say that the support count of Tx is 3 because X is repeated 3 times in the data set. X is repeated in T1, T2, and T3. So the support count of the support count of X is 3. And support count of XY is 2. Equilat is presented in KDD 97 conference. However, by Zaki and his colleagues, they complete their methods in STM 2002 conference, and they present charm algorithm. Unfortunately, here we have not a good example in the slides. In the book, you can find a good example about this to find how we can use equilats to calculate the frequent items. In page, let me just wait a second, please. This section 6 to 5. In page 260 of the book, in page 260 of the book, you can find So, to find a good example for ECLAT, please read page 260 of the book, of the textbook. There's a good example for ECLAT. If you read section 6.2 of the book, it has a good example, and the others try to find the frequent patterns using a priori, FPGrowth, and ECLATs. In section 6.2 of the book, you can find a dataset, a small dataset, and the others apply a priori, FPGrowth, and ECLATs on that dataset to find the frequent patterns. Please read this section carefully. Okay. But okay. Okay, for example, here the others try to talk more about some other related algorithms. For example, in closed set, primary in the first step in closed set algorithm. Firstly, we create a F list, a list of frequent items. This list is sorted according to their support values in ascending manner. For example, here, if we have this data set, this is small data set with minimum support of 2. With different items, I can see that D is D, A, F, E, and C are frequent items in this small data set. This list is sorted in an ascending manner. Then we can divide and search the space, for example, for patterns with D and something like that. And we can use our past knowledge to find, for example, closed pattern. We can do this using a recursive function. Okay, I'm passing these algorithms, but you can find more details about them in the internet. For example, closed set plus, max minor, and charm, and rest of them. For example, charm is presented by the others who presents the eclat. So if you look at this slide, you can see that the content of this slide is similar to the content of eclat slide because they are similar together. Okay, we can visualize the association rules or frequent patterns in different using different techniques to present relations between different items. For example, something like this. But until now, we try to find frequent items. It's not important for us until right now. It's not important for us which of those algorithms we are using to find frequent item sets. It's not important for us. Okay, so we find here, we suppose that we find frequent item sets. Okay, so right now, one main question is that, okay, I found these frequent item sets, but what is next? Is this frequent item useful for me? Yes or no? I found them. I found a list of frequent items. But are they useful? Yes or no? To answer this question, we should go ahead. For example, we have a data set asking from some questions from different students. We ask them, for example, are you playing basketball? They say yes or no. And also we ask them, are you eating krill? They say yes or no. And we create this table. We fill the answers in this table. For example, here I can see that 2000 of the students say that they are playing basketball and eating krill. 1000 say that they are playing basketball but they don't eat krill. 1750 students say that they don't play basketball but they eat krill, and 250 students say that they don't play basketball and they don't eat krill. Okay, let's suppose that I'm looking in the data set, I'm looking for frequent items, and I found that play basketball and eat krill is a frequent item, and I can't look at this frequent item as a rule, as an association rule. We talked about association rule last week. This rule has 40% support and 66.7% confidence. Okay, I'm repeating again. I have a data set from different students, and I search in this data set, and I'm finding frequent item sets. For example, I found that I have a relation between playing basketball and eating krill. With 40% support and 66.7% of here we can see that the support count of playing basketball and eating krill is 40%, but overall 75% of students are eating krill. But here, the confidence value of playing basketball and eating krill is 66.7. That is interesting here, that overall 75% of students say that they are eating krill, but here the confidence value of this rule is less than 75%. But look at this rule. If playing basketball and not eating krill, the support value is 20% and its confidence is 33.3%. For not, how? In the past week, we talked about support and confidence values, Hana. We talked about supports and confidence, and we say that to find support, we should count number of times that we can see if we can see an item. We can see an item, and okay. Here, we say that if we shoot number of times that an item is appeared in the data set is support, okay, or we can say it using probability of or support of X. If we have a rule in this manner, X then Y, its support is X union with Y, and So we calculate these items. Here, for not eating krill, we can see that only 25% of students say that they don't eat krill. And here, the rule playing basketball and not eating krill has confidence of 33.3. Although the first rule has higher support and higher confidence values, higher supports and confidence values. But we can say here, we are saying that the second rule is more accurate than the first one. Although it has lower support and confidence, but it's more accurate because it's near to the values in this table. So we need to calculate the dependency or the correlation between items in a rule with facts in the dataset. One of the well-known and public measures to calculate this correlation, this dependency, is lift measure. The lift measure between two items A and B, or X and Y, I don't know, is using this. Lift of A and B is probability of A union B divided by P of A times in P of B. For example, here, lift of playing basketball and eating krill. Here, the first rule. Playing basketball and eating krill. If we use playing basketball and eating krill, we can see 2,000 from 5,000 students are playing basketball and eating krill. So the probability of A union by B is 2,000 divided by 5,000. And P of A, probability of playing basketball, is 3,000 divided by 5,000. And P of B, eating krill, is 3,750 divided by 5,000. We can see the lift value for playing basketball for the first rule, playing basketball and eating krill, is 0.89. 0.89. In the same manner, we can calculate the lift for the second rule, playing basketball but not eating krill. And we can see that the result for the lift value for the second rule is 1.33. Okay. It shows that the second rule is much better than the first rule. It's much better than the first rule. Why? Because its lift value is higher than the lift value of the first rule. Here in slide 54, you can see different measures, different metrics that they can be used as a good measure to calculate this correlation. For example, here, lift is placing here in this table. You can see Chi2 metrics, all confidence, quotient, confidence, support, Gini index, J measure, and other metrics here. Over 20 interesting measures have been proposed to find these correlations. But which of these measures is better than the rest? Which of these measures? We have different measures. You can find them in section 633 in the book. In section 6.3.3, you can find these measures. Okay, but the main question is this: which of them is better than the rest? Here, in slide 55, you can see some features for measures, some properties here. Symmetry under variable permutation, row and columns, scaling invariant, and so on. In property 5, you can see the property null invariance. Here, in this table, row 04. Row 04 is property null invariant. You can see only confidence, quotient, and Jacquard measures. Only confidence, quotient, and Jacquard metrics all are null invariant. But what is null invariant? What is null invariant? Also, we have other metrics too. For example, here you can Klejansky measure is missing here. Let me talk about null invariant in this example. Using this example, I want to talk about null invariant impact on all measures. We have here 7 different measures to calculate the correlation the interesting value for a frequent pattern. These measures are K2, lift, all confidence, confidence, quotient, Klejansky, and max confidence. And you can see their definitions here in the second column. Also, their results, Kaido and lift. Kaido and lift are positive, but all confidence, coherence, quotient, Klejansky, and max confidence only can have a value between 0 to 1. And you can see chi2 and lift are not null invariant, but rest of these items are null invariant. Okay, to talk about the property null invariant, let me talk about this table here. We ask questions from different peoples. Are you eating milk? Are you eating coffee? Someone say that, okay, I'm eating milk. Someone says, no, I don't like milk. And someone say that I like coffee, and someone say that I don't like coffee. Okay, we create this table with different items. Liking milk and coffee, don't like milk but like coffee, like milk and don't like coffee, don't like coffee and don't like milk. 4 different choices, 4 different combinations. Here in table 2, we have 4 different rows, 4 different columns. Under each of these columns, you can see different values. For example, in the dataset D1, we have 10,000 people that they say that, okay, I like coffee and I like milk. 1,000 people say that I don't like milk but I like coffee. 1,000 say that I like coffee but I don't like I like milk but I don't like coffee, and 100,000 people say that I don't like coffee and I don't like milk. Okay, we have 6 different data sets here, 6 different data sets, and you can see that for each data set we have different number of values for each of those 4 columns. Okay, using these definitions we calculate the values chi2, lift, all confidence, coherence, Gaussian, Koleshinsky, and max confidence for each of these datasets. Look at the result in this table. Look at the result. Here you can see that, for example, for D2, we can see that most of people say that I don't like milk and I don't like coffee. 100,000 of those people who are that we asked them. Most of people are grouped into this category. Don't like milk and don't like coffee. Look at the chi2 value, 9,557. The lift value is 9.26. All confidence 0.91, coherence 0.83, Gaussian 0.91, Koleshinsky 0.91, max confidence 0.91. In D2, most of people say that they like coffee and they like milk. Just a few people say that they don't like both of them. We can see everything has been changed. In the first data set, most of people say that they don't like coffee and they don't like milk. But in the second data set, just a few people say that they like coffee, they don't like coffee, and they don't like milk too. But look at K2 and lift value. You can see there is a big difference between K2 values and lift values. But for the rest measures, look at this. All confidence is fixed, coherency, Gaussian, Kolodzinski, and max confidence. You can see the rest measures does not affected by these values. In the first data sets, most of the people are grouped into the class don't like milk and don't like coffee. In the second data set, this class is minority. Just a few people say that they don't like coffee and they don't like milk. And you can see that the lift value and K2 value are changed rapidly. This is the impact of null invariant. Null invariant means that I have a class or a group with a few numbers of objects or with too much numbers. A null invariant property says that our measure does not affected by something like this, affected by a very small group or a very large group. You can see that K2 and lift are not null invariant. And here we can see the result. Their values changed sharply. But the rest of these measures are null invariant. They have null invariant property. So they does not affect it. But which of them is better? In D3 to D6 datasets, we test another combinations of values for milk and coffee here. And as I see here, I can see our confidence is changed for different data sets. Coherency is changed. Gaussian is changed. Max confidence is changed in some cases. But the most robust result is dedicated to Kolodzinski measures. The Kolodzinski measure has the most robust values. Look at this D4 to D6. Okay, I will finish it. Just in a few minutes, I will finish it. Look at D4 to D6. The values for 3 of those classes has been changed. And you can see the Kolodzinski matrix does not affect it too much. But the rest of measures affect it. So Kolodzinski is one of the best measures in this case. Okay. So non-invariant measure is an important measure for us. But how we can say that when, for example, using Kolodzinski is better than using lift value. For example, in Veka, you can the Veka calculates the lift value for you, but it does not calculate Kolodzinski value. When we need to use Kolodzinski measure or something like that, using a null variant measure. To do this, we are defining a measure IR or imbalance ratio. We say that if two item sets A and B are imbalanced, then we have to use null invariant measures. Imbalance ratio of A and B is calculated using this formula. And as you can see that this formula consists of support value between A and B. So for an imbalanced data set, imbalance means that most of objects are grouped into into one or a few classes, and we have some groups with a few number of objects. Most of objects are grouped into one or two. For example, big class, and there are some classes with a few items. For example, here we have a class with 1,000 item, and we have a class with 10 or 100 items. This data set is imbalance. So when our data set is imbalance, to talk about the quality of our patterns, which of those patterns are interesting. To talk about them, we have to use null invariant measures if we want to present a good result. So Kolodzinski is better than lift or K2 measure for imbalanced data sets. Okay, our class is finished. But let me talk about one more things. Okay. Is a frequent item always useful? Sometimes yes, sometimes no. It depends on our goal. For example, selling jewelry and gold. Most of people tries to buy gold, but jewelries are more expensive than gold. So just a few people tries to buy jewelries. But if someone buy jewelry, it has more benefits for me. If I'm a jewelry seller, and I'm selling jewelry to someone, my profit is higher than when I'm selling gold. But total number of people who are interested to jewelry and buying jewelry is very low. So sometimes, according to our goals, sometimes finding frequent patterns may not be interested. Sometimes finding records with not frequent items, not frequent patterns, and minor items maybe are more interesting for me. So at the end of this chapter, I should repeat this. Most of times, frequent patterns are important and useful, but not always. Sometimes infrequent patterns are useful for me. Why? It depends to our goals, to our data mining project. Okay. Thank you for joining the class. I wish the best for you. Have you any question? Have you any question?